All right, hi, good afternoon. This is my first set of notes from Chapter 7, VLE of Pure Fluids. And this set of notes will focus on kind of an introduction or motivation of the chapter, and then we'll briefly talk about enthalpy of vaporization. Okay, so the first few slides will be review, but will be important to make sure we have a firm understanding before digging deeper in the chapter. Okay, so first, homogeneous closed system. Okay. So homogeneous means that if I were to take a sample, so let this red box be me taking a sample at random throughout my system, that wherever I take a measurement, that those properties of that system are going to be exactly the same. So homogeneous, the properties are uniform or the same throughout. Closed, so by this black border, what I mean is that mass and moles can't cross my phase boundary. Okay, so we can exchange heat and work with our surroundings, but mass, so the total number of moles in the mass of my system is going to be constant. It can't cross my phase boundary. Okay. Homogeneous open system. So homogeneous, again, if I was to take a sample at random throughout my system, the properties would be the same in every single one of those samples. So the properties are uniform throughout. It's open, okay, and now indicate this with this dotted borderline up here. It's open in that mass or moles can now cross my system boundary. Okay, so the mass and moles are no longer constant. Heterogeneous closed system. So now we have this first keyword, heterogeneous. And so what that means is if I were to take a sample at random throughout my system, that the properties would not be the same. Okay, and so here I have a system composed of a phase 1 and phase 2, right? Maybe this is a vapor and it's a liquid. So the idea is if I take a sample at random throughout phase 1, right, the properties are going to be the same, right? Phase 1 will be homogeneous. If I were to take a sample at random throughout phase 2, the properties there are homogeneous, okay? But a sample from phase 1 is not the same as a sample from phase 2, okay? So if this solid black border sets my system boundary, okay, then my properties are not uniform throughout because the properties of phase 1 are different than from phase 2. Okay, it's closed though, where if I take this to be my system, mass and moles can't cross this solid black boundary. Okay, another buzzword that we'll come back to later is a heterogeneous closed system like this is often called a composite system. A composite system consisting of two homogeneous open systems. Okay, so if I were to look just at phase 1, okay, properties are uniform throughout. All right, it's homogeneous. It's open, just like the past slide, in that mass can cross in my phase 1 boundary. Okay, same thing with phase 2. What makes them special though is that any mass that leaves phase 1 would go to phase 2. Any mass that leaves phase 2 would go to phase 1. Okay, and we'll come back to this later on when we derive our criteria of phase coexistence. But for now, heterogeneous closed system, properties are not uniform throughout, and it's still closed, and that mass can't cross my overall system boundary. Okay. So remember, a main motivation of this class is modeling phase behavior. And by phase behavior, I mean we're going to focus on vapor-liquid coexistence, but kind of the same principles would carry on to solid-liquid, liquid-liquid, and whatever else have you. Okay, and so the main motivation is, we live in a world of mixtures. Separation processes are essential to our daily lives, right? Whether it's the air I breathe in, that's mostly a mixture of nitrogen and oxygen, so I breathe that into my lungs, and then I need to preferentially absorb oxygen into my blood, or the many other applications that you can think about. From an industrial standpoint, 40 to 70% of the capital and operating costs of a chemical plant is separations. So if you graduate and go to a traditional chemical engineering job, right, separations are a major capital and operating cost of your job, right? And if 40 to 70% of the capital and operating costs are rooted in separations, it stands that, hey, if I am really, really good at separations, if I have a really good understanding of the underlying thermodynamics, any small improvement I can make to that separation could lead to a huge cost savings for your company, right? And I have this stat here for traditional chemical industries, but even biological industries and what other applications you're looking at, separations are still going to be really, really, really important. Okay. So a picture you might have, again, from a traditional chemical plant is that your chemical plant is essentially just a reactor. You could think of the reactor as the heart of the process, but it's going to be surrounded by separation processes. Okay. So typically, right, I have some stream of raw materials. I need to prepare those reactants for my reactor. So maybe there's some undesired reactant I need to remove that would otherwise poison my catalyst in my reaction step. And then after the reaction, I need to take whatever product stream leaves the reactor and ultimately formulate it and deliver it for a given application. So before we start to talk about VLE, I want to look back at our PV phase diagram. Okay, the key take home here is I have pressure plotted against molar volume. Remember, when I'm talking about phase coexistence, we have thermal, mechanical, and chemical equilibria. Thermal equilibria tells us that the temperature of my two phases in coexistence are equal. Okay, there's no desire to exchange or net exchange of heat between the two phases. I have mechanical equilibrium. The pressure of the two phases are equal. There's no desire to exchange PV boundary work between those two phases. And then chemical equilibrium, so that's your mass transfer class. I have an equality of chemical potentials of each species in each fluid or each phase. So there's no net rate of mass transfer between the two phases. Okay, but for now, if we just think about equality of temperatures and pressure, temperature and pressure of my two phases in coexistence are equal to each other. Okay, so when I look at my PV phase diagram, okay, I have a phase envelope, all right? So underneath the phase envelope, I have two phase. To the left, I have a liquid. To the right, I have a vapor. Okay, and so why I have a dome is, well, at two-phase coexistence, the pressure of those two phases are the same. Okay, if I follow along an isotherm, it's flat along my phase envelope or across my phase envelope because the temperature is the same in the two phases, but molar volume is not. Okay, so temperature and pressure are the same in the two phases, as are chemical potential, which we'll get to later. Okay. So the next thing I want to talk about is enthalpy of vaporization. So the first topic in this chapter. Okay. So the enthalpy of vaporization is just equal to the enthalpy of my vapor minus the enthalpy of the liquid. So when you think about enthalpy of vaporization, think about the process of vaporizing something. Okay, so the process of vaporizing something is taking a liquid and making it a vapor. Okay, so if I want to calculate the change in enthalpy or the change in energy for that process, I'm going to take the energy or enthalpy of my final state and subtract from that the energy or enthalpy of my initial state. So it's enthalpy of my vapor minus enthalpy of my liquid, final minus initial. Okay, cool. Enthalpy of vaporization is going to correspond to two phases at coexistence. So if I have water at 1 bar, we know it boils at 100 degrees C. So what's the enthalpy of vaporization, or the change in enthalpy of going from a liquid to vapor at that pressure, right? Pressure or temperature, however you want to characterize things. Okay. So my vapor and liquid correspond to two phases at coexistence. From the last slide, we said if I have two phases at coexistence, they're at the same temperature and pressure. Okay. So what I have written here as an equivalent expression is, well, if these are at the same temperature, I could take my enthalpy and I could write it as the sum of an ideal gas and a residual contribution. Right? I could do that for both my vapor and my liquid phase. Well, my ideal gas term is only a function of temperature. So if both of these are at the same temperature, the ideal gas term conveniently cancels out. And so what I'm left with is I could equivalently write this as the enthalpy of vaporization is just equal to the residual enthalpy of my vapor relative to the residual enthalpy of the liquid. Okay, cool. Okay, so the note here is for historical purposes. So we call this enthalpy of vaporization, which makes the most sense to me because I can picture what that means physically. But historically, enthalpy of vaporization sometimes referred to the latent heat of vaporization. So if you see latent heat of vaporization, it means exactly the same thing, right? It's more of an older historical term, if you will. Okay. So question, right? So we said molecular thermodynamics is going to be important in this class. So will the enthalpy of vaporization be positive or negative? So take a second and think about it. Okay. And we had looked at essentially the same example back in chapter 1. Right? And so now the idea is H, right? H is going to be equal to U plus PV. So if temperature and pressure are those two phases, right, I could essentially write delta H as being delta U plus P delta V. Right? Or I guess it would be, plus P delta V. So if I think about going from a liquid to a vapor, well, I know delta V is going to be positive because I'm going from a liquid to vapor, and I know the spacing between molecules in my vapor is much greater than my liquid. And if I think about U, okay, I'm going from a liquid to vapor. In a liquid, all my molecules are really, 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 really close together. Okay, those are favorable, attractive interactions. When I vaporize it, I'm now separating all those molecules to much further distance. Okay, so if I think about my LJ potential, I go from somewhere close to the well of my LJ potential to some interaction or some potential energy that's close to zero being infinite separation and ideal gas. So delta U of vaporization is going to be positive, and delta V of vaporization will also be positive. Should also make sense though, because if I just think about what's happening and going from a liquid to vapor is, hey, I need to add energy to separate those molecules to vaporize them. Okay, cool. So both of those terms are going to be zero. Delta H of vaporization is greater than zero. Okay. Another example I always like to talk about in class is, phase changes have lots of actual practical applications. One that maybe you've never consciously thought about is, why do you sweat? So as human beings, we sweat. Me being one person that sweats more than others, right? So sweating is a natural mechanism to cool yourself. So the idea is I perspirate, I get liquid on my skin, okay, and then, essentially that liquid's going to be vaporized, right? It takes energy to vaporize that liquid water. That energy is being extracted from my body, right? So it's cooling me off. So I perspirate, so I get wet, right? And then the idea is in order to heat that water to vaporize it, heat's being extracted from my body, which results in me essentially cooling off, right? And I can't remember the exact source or things of that nature, but I remember reading at one time very long ago that apparently one of Ben Franklin's first inventions was, discovering that if he wore a wet sweater in the summer, that would actually cool him off, and this is the exact mechanism. Okay, you don't want to see my Google Calendar notices. And so enthalpy of vaporization is a useful property to calculate, and so we'll just look at two common methods to calculate it. One for historical reasons is called Troughton's rule. And so what Troughton did is he was alive, I believe it's the early 1900s or late 1800s. But regardless, Troughton had a set of experimental data of enthalpy of vaporization at normal boiling point and then Tn, normal boiling point. And what he found is that for for all the fluids that he had, that if he computed the ratio delta H of vaporization N, so this is enthalpy of vaporization at the normal boiling point over Rtn. So what's the normal boiling point? So that'd be my saturation temperature at 1 atm, or 1 bar. So if he computed the ratio delta H over Rt, which is dimensionless, that for all of his fluids, it appeared that that was approximately equal to 10. Okay, so Troughton's rule is delta H of vaporization over Rt at the normal boiling point is approximately equal to 10. So what does this do for me? Well, if I know the normal boiling point, this gives me a way to approximate delta H. Okay. Another very common or very powerful technique is Watson's equation. And so I've actually seen some physical justification for Watson's equation. And so what we have here is this is the ratio of enthalpy of vaporization at two different conditions. And, so remember, enthalpy of vaporization is going to correspond to vapor-liquid coexistence. So if I say this is at some T2 and that's at some T1, Remember, the pressures are different too, right? But they're dictated by that temperature. Okay, so if we were to just call them temperatures, at saturation, enthalpy of vaporization at some temperature 2 relative to enthalpy of vaporization at some temperature 1 is equal to 1 minus the reduced temperature at state 2 divided by 1 minus the reduced temperature at state 1 raised to the constant C. So reduced temperature, remember, is T divided by Tc. Value of C, so common term is either 0.38 or 0.375. Okay, and so this expression works incredibly well. If I have knowledge of the enthalpy of vaporization at one condition, and I know my critical temperature, okay, I can use this to make very accurate predictions at other neighboring conditions. Okay, so the way it would work is I know, say, enthalpy of vaporization at some state 1. I know my critical temperature, and I know T1 at, say, my reference state. Okay, and so that if I want to predict the value at some state 2, all I need is its temperature. I can plug it into the right-hand side. I know this term. It gives me a way to solve for delta H of vaporization at state 2. And so this does incredibly well in terms of correlating enthalpy of vaporization from the critical point all the way down to the triple point, and works really, 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 really well in predictive mode if I have one reference value. Okay. In fact, I use Yaw's handbook a lot for property prediction. If I want to predict or calculate the enthalpy of vaporization at some conditions, I would typically look at Yaw's handbook. The correlation that Yaw's actually uses for enthalpy of vaporization is just Watson's equation. He just slightly modifies it so that he also changes C into an adjustable parameter, which he fine-tunes based on a series of reference data that he has. Okay, so it's still widely used, is very, very good, and is very powerful. Right? It's kind of in that category with Racket equation where it just works really well. And again, I've seen a number of studies recently where folks have actually tried to physically justify this constant in the form of Watson's equation altogether. Okay. Again, we've talked about two kind of common or popular methods for estimating enthalpy of vaporization. In general, I would try and avoid Troutman's rule unless I had nothing else available to me. But just like cubic equations of state, if you ever need to estimate enthalpy of vaporization, this is another one of those things where, okay, I need to estimate a property. What method do I use? The answer is, well, it's kind of based on experience, right? Again, that's why when you get a job, you get paid more the longer you're at a company, right? Because you build up more of this experience, and predicting enthalpy of vaporization is exactly the same. Okay, and so I've referred you before to this properties of gases and liquids by Pauling, Process, and O'Connell. So chapter 7 is all about calculating enthalpy of vaporization. All right, so here's section 7.2, discussion and recommendations for enthalpy of vaporization. So what they've done in this book is they've taken all of these common methods to calculate enthalpy of vaporization, including from cubic equations of state. They evaluate them for calculating enthalpy of vaporization for a wide range of systems, and then based on all these observations, they're able to make recommendations. Right? So it's the same as, these are folks with lots of experience. They've tested these things out on lots of systems, and based on that, they're able to make recommendations. Okay, and so that wraps up the first set of notes for Chapter 7.